Welcome back to Differential Calculus. This video is vaguely titled Applications of Integration. I want to look at two specific types of applications, both of which we have talked about previously. But now that we have all of the tools for evaluating definite integrals, I want to revisit them and look at some more interesting practical applications. The first one is area under a curve. The problem asks us to calculate the area of the region bounded between the curve y equals 4 minus x squared and the x-axis. In order to calculate this region, we're going to start off by graphing it. You could, of course, use Desmos or something like that to sketch the graph of the function if you so desire, but this one is fairly straightforward. Right? It's an x squared, it's a parabola, it's negative, so it's opening downward, and the y-intercept is at 0, 4. So we just go ahead and plot 0, 4. We plot a couple of points around that. And we get this parabola that looks something like that. We also have the x-axis, which is right there. And we're asked to find the area of the region bounded between these things, which is that space. Analytically, I know that the area bounded between, or bounded underneath a curve is the integral of that function. Well, I have to know now that the x-intercepts are at -2 and +2, but again, just setting 4 minus x equal to 0 and solving for there is fairly straightforward. So this will be the integral from -2 to 2 of 4 minus x squared dx. An antiderivative of 4 minus x squared, 4x minus 1/3 x cubed. Evaluate that at our limits of integration. We will have 4 times 2 minus 1/3 times 2 cubed minus 4 times -2 minus 1/3 times -2 cubed. You could use a calculator from here, but the arithmetic is fairly straightforward. We have 8 minus 8/3 plus 8, right? Minus a minus is plus, and then we have minus a minus a minus, which is going to end up being minus 8/3, which is 16 minus 16/3. Let's see, common denominator, 3 times 16 is 48. And 48 minus 16 is 32. So the area underneath this curve is 32/3. Again, with a calculator's help, you could just go from there straight to the result, but I wanted a fractional value, and my calculator probably would have given me a decimal instead here. The other application I want to look at in this video is mass and density. We talked about density and accumulation functions previously, and we never really got a solid application on them because we didn't really have the tools. Now we do, so let's address that. Consider a thin rod made of a material with non-uniform linear density, rho of x, right? The Greek letter rho is commonly used to represent a density. Rho of x is 2x times the square root of x. We want to calculate the total mass of a rod that is built from x equals 0 to x equals 12. Right? So we know that the total mass is going to be the accumulation function from the starting point 0 to the ending point 12 of our density function, which is 2x square root of x dx. Actually, performing this integration, it might be a little bit easier to rewrite that using some exponents, right? X times the square root of x is x to the 3/2 power. And with that, we can use the power rule a little bit more cleanly. We're going to have, I guess it would be 3/2 plus 1 is 5/2. So divide by 5/2 is the same thing as multiplying by 2/5. We have 2 times 2/5, which is 4/5, times x to the 5/2 power. All right, evaluate that at 12, evaluate that at 0. The square root of 12 is 2 square roots of 3. 2 to the 5th power is 32. 3 to the 5th power is 243. So we'll have 32 times 4, which is 128, over 5, times the square root of 243. That's an answer only a mathematician could love. If you happen to have a calculator and you want to plug that into a calculator instead and get a decimal approximation, you are more than welcome to. This should come out somewhere in the ballpark of 400, 450, somewhere thereabouts. I don't have my calculator on hand, so I'll leave it at that. Right? I am a mathematician, so I will accept an answer only a mathematician can love. Right. I'd like you to try one similar to this. We've done area problems before, so I know you know how to set up the integral. We haven't really done mass and density functions before, so we'll get some more practice on that. Consider a thin rod made of material with non-linear density. Rho of x equals the square root of 9 minus x. Calculate the total mass of such a rod arranged from x equals 0 to x equals 9. All right, the actual calculus on this one will be a little bit trickier than the one I went through, but still not too difficult for you at this point in the course. I'd like you to take a couple of minutes, see what you can do with that one, and I'll see you in the next video.